Shall we start? Okay. So, what did we establish? In the first part, we established the importance of the Banach contraction principle. And the role, in other words, moving forward, I have no doubt in my mind, you will never look at the Banach contraction principle the same way as before. Now, you are looking at it with a totally different what? View. Okay? Why is it important? What is it in it? Beyond the conclusion. Beyond the conclusion that was known. It's not like something that Banach discovered. In fact, what I told you was known to Banach. It was something known to him. It's what people try to make it as a conclusion from the Banach. Okay, great. So now we established this. So the question becomes now, how can we go beyond Banach? So again, Banach contraction principle is the concept of these tools implied or used in this abstract form of metric spaces. So people, they wanted to extend it. And there were many ways to extend it. One is to extend the Lipschitz condition. Okay? So from 1922 to 1965, people did come up with new classes of mappings. Like, of course, I'm thinking about canon maps. What's his name? The Gasseric maps, and so on and so on. So there were tons of publications trying to extend the contraction condition. Okay? That's one route. Second route is the metric. How can we preserve? It's the same, by the way, huh? All of them. They all get the iteration that behaves nicely and converged, but the conditions are different. So, for example, can we change the structure, come up with a more general structure? So one route that Professor Dhage has taken, and others, is the idea of looking at an abstract structure, more abstract than metric spaces. Okay? So what's interesting is, first of all, why is that? Why do we want to find, let's not talk about the conditions on the maps. Okay? I will not be talking about this here. I mean, in this course. I want to focus on the structure, the metric space structure, okay? As a continuity to my question, what's made him the theorem famous? Okay? What's made the theorem? So, first of all, shall we question the three axioms? Okay? Shall we question the three axioms? When was it published, the three axioms? You know the answer. When? Axiom 1, 2, 3 for a metric space. When were they published? 19? I mean, if I give you a quiz now, what's going to happen? Failing totally, Wallahi, I came 2 days ago, I ate some very spicy food. My stomach is not feeling well. Wallahi. I swear. It's not feeling well at all. So it was 1914. So remember, 1906 was our friend, what's his name? Fréchet. But Fréchet did not give the axiom 1 and 2 and 3 in the abstract setting with the concept of metric and distance. Okay? It was done in a formal way by Osborne. And again, some people were confused. I'm really sorry. So let me show it to you. Some people were confused about the distance between two sets. They thought that this is the distance. That's not the distance. Distance, let me try to go a little bit faster. See it? So, I'm sorry. So you see, this is how you define. This is known the distance between the green one and the other one. Huh? So it's the supremum of the infimum and the supremum of the infimum. You reverse it, and you take the max. Okay? So that's the distance between the two sets. This Hausdorff distance is also called Pompeiu. These are the Romanians. They insist to say that it was known to Pompeiu as well. Okay? Okay, so this is based on what's known as the epsilon neighborhood of a set, okay? And you take the supremum of all this. But anyway, so it's complicated. It's not what I was showing you. That's the common sense, but it's not. You see the definition? Huh? Max sup of the two to make it symmetric. I'm talking about this one here. This one. And there is still open questions about it. Yeah. In the case of multi-valued mappings. Because they assume that both of them are kind of bound. Anyway, well, let's move on. That's not the purpose of this class. I want to take you to some other level. Okay. Yeah? No, not this way. This way. So, the issue was about questioning axiom 1, 2, and 3. I already talked about 3, the triangle inequality. Okay? What if you don't have the triangle? And you have to understand that questioning axiom 1, 2, and 3 is not like for the sake of questioning. It's not only for the sake of coming up with some more general structure. I'll give you an example and you will understand. Okay? What's known as the flower shop problem in computer science. Okay? The flower shop problem in computer science. So let's say you want to buy flowers. We are celebrating what's the name? On the 14th of February. What is it called? Huh? What is it? What is it? What is it? Huh? You are unbelievable. Oh my, you are unbelievable. So, I'm celebrating my wife's birthday. And I need to buy some flowers. So, I go to the flower shop. Okay? And leaving my home, going to the flower shop. Okay? I can compute the distance between my home and the flower. Question. Will the distance from my flower shop or the flower shop to my home will be the same? Very simple. Yes or no? The answer is it will not be the same. Therefore, the distance from A to B is not the same as B to A. Why? And I gave you the answer earlier. We have axiom 1, 2, and 3. Okay? I gave you the answer. So remember axiom 1, 2, and 3 from Hausdorff. He found it where? Published by Fréchet. And Fréchet got it from where? The question from Adamar was what? To find the écart or the distance between two functions. And because you are looking at two functions, or the distances on functions, we think about them this way. We look at their value. Sorry. We have f of x, g of x, and natural, if they are real valued, to consider the distance between f of x and g of x. That's the absolute value of f of x minus g of x. And then you do whatever you want with that. Okay? Whether you consider L2 norm, or whether you consider sup norm, whatever. But the ingredient is absolute value of f of x minus g of x. Therefore, the essence for functions is coming from the absolute value between the difference between two numbers on the real line. And using the properties of the absolute value gives me the three axes. You see it now? And if you want to extend it to R2, R3, R4, you use what? The Euclidean distance. Anyway, the point is, okay, we have these three axes. Okay? Axiom number one fails. For what? Not for the flower shop. Flower shop is natural. It's just to understand that it's not true. Distance from A to B is the same as distance from B to A. Okay? But even during the time of our friend, what's his name? Choquet, Frechet and others, they were looking at two functions. Yeah. So if the two functions, they have a distance equal to 0, they get f and g are equal almost everywhere. They are not equal. So there is a problem. It's really that Lebesgue measure complicated the matter completely. Okay? Now, axiom number two, sorry. Axiom number one, we have a problem. Axiom number two, we have a problem. Symmetry. And finally, axiom number three, the triangle inequality. Also, we have a problem. Sometimes we have what's known as, we have a constant. Instead of distance less or equal than distance plus distance, we have a number there. Okay? Early on. I'm not talking about fictional. Now, some generalizations are interesting because they answer a problem. Some generalizations are created for the sake of using the ingredient of the proof of the Banach contraction. Try to understand what I'm saying, okay? Please. Some generalizations are trying to understand a problem, and I will tell you one that took me 30 years to answer. With respect to this, I will show you something. Some, you are looking at the fundamental problem, and you're trying to answer that problem. And you couldn't answer the problem within the framework of classical metric. Understand now? So we come up with this what? More general structure to try to understand. That is exactly what Banach did with his Banach contraction plan. Understand? He didn't invent the theorem in terms of tools. He just tried to see something that is more general than the case of what? Functions, the case of what? Sets. Okay? And other examples. But sometimes we have some generalizations that are, they lead to the application of what? Of the tools, iteration, convergence, and so on. Sometimes the problem with this, and this is where I want to come to the work by Professor Dhage, is that sometimes, and this happens to all of us, I'll tell you, papers were published. And I'll explain, because in this course, I will be talking about this. So it's very important about what's known as modular vector space. So the problem is what? When you extend, your brain is programmed to think in terms of what? Metric spaces. You understand now? So when you come up with this general structure, you have to disconnect completely from what you learn. For example, to clarify my point. Let's say you don't have the triangle inequality. You don't have the triangle inequality. You lose the uniqueness of the limit. Right there. Okay, fine. What if I am not symmetric? Distance from A to B is not the same as distance from B to A, which is natural, by the way. And I'll come back to the flower shop problem. If that's the case, then wait a minute. Like matrices and products of matrices, you have to be careful. What goes to the left? What goes to the right? If that's the case, the limit, now you have a concept of what? Left limit and right limit. So if you don't take yourself out and disconnect your brain from what you learn in the case of classical metric spaces, you will fall into what? Some basic mistakes. This happens to all of us. All of us. No exception. So for example, the module I talked about it yesterday, the module does not satisfy the inequality, the triangle inequality. And I have seen papers published by our group in Thailand, okay? They told them about modular spaces, and they did not pay attention, and they did a theorem, and they published it. And of course, they did not pay attention that they were using ideas from the classical metric spaces in their mind without being careful. You see what I'm trying to say? So this happens to the best among us. So in the work done by Taipei, he got some results, and with one assumption, which is valid in the case of what? The metric topology, but is not valid in D metric spaces, according to his definition. Okay? It was not valid. Okay? So this happens. No big deal. Now, why am I talking about this? Not because Professor Haji is here today. No. In fact, I was surprised what his name, Javid, told me. Oh, he's coming. Oh, I was so pleased. Finally meet him. I have been talking about him worldwide. And I really mean it. Worldwide. Name it, I'll tell you where. I mean, everywhere in the world, I was talking about him. So, what happened? My friend, Brayley, okay, who is a big name in functional analysis, okay, as well as in fixed point theory and metric fixed point theory. And he came to know about the publication by Professor Dhage on D-metric spaces. And he saw that there is a problem, okay? But it wasn't like, big deal. That's it. It was a problem, okay? And at the same time, a little bit shortly after that, a student from Jordan came to Australia to visit, not to visit, but to study with Brayley. And Brayley killed him laterally. Okay? And you will see some other examples during the course where you can kill a young mathematician forever. And they will explain to you how. And it's not given to everybody to have the ability to accept a challenge and move on and better yourself. Sometimes when you are young and you hear or something happens to you, it can kill your career completely. So the case of Ziad, he asked him to look at this D-metric space. And finally, they fixed it. Okay? And they came up with a structure that was the essence answering that question. So it was something that he called, I wish he called it D-metric spaces. He did not call them D-metric spaces. He called them so he called them, as you see here, G metric spaces. Okay? Fine. If I were his advisor, I wouldn't have let him do G metric space. I would have said D metric spaces or revised D metric spaces, because that's what it is anyway. So, G metric spaces. Not only they do these G metric spaces, then they went and they proved the theorems, the basic theorems that did not work in the case of D metric structure, but now they work in the G metric space. Okay? So this is the definition. Don't worry about it. Just to show you. This is the definition of what is a G structure. Okay? So it's more general than what? A D structure. Okay? Don't worry about it. Don't worry about it. It's not really. So now, few questions. Very important. That I want you to ask yourself. Okay? And I will explain to you why Ziad was killed. Okay? I'll explain to you in a second. So, number one, I need to find out this structure, because remember what Banach did. Banach contraction principle, he learned from what? Hausdorff book that was circulating, by the way. And he took the structure of metric space, and he took the theorem that was known in different contexts, and he said this is more general. Okay. And then we found some amazing applications of that. You understand? In the case of fitting, and in the case of other structures, okay, where the tool of metric space became important, took more and more center stage in what? In mathematics. Okay. In this case, they did not offer a motivation or an example that will enrich the structure of a metric. So what did they do then? All of their results are in terms of geometric space. Geometric space. If we have geometric space, if we have this, we have this. We have this, we have this. Theorem 1, Theorem 2, Theorem 100, Theorem 200. You are talking about everybody. Now, they took the body of fixed point theory, and they try, the body, all of it, and they try to do it in terms of what? Of G structure. Okay? So, of course, what happened is Ziad became famous. Why? Because once everybody wants to do and work on geometric spaces, you have to refer to whom? Not to the Hajj. No. You are referring to the guy who gave the definition of what is a geometry. You understand now why is G not revised D? Did you get the subtle message I'm trying to convey to you? Because once you do that, you have to be a little bit sneaky. You have to be a little bit dirty. If you want to stop citing someone, you will come up with something, you come up with something. Once you come up with something, everybody will what? Refer to what? To you. So our friend became extremely famous. In fact, in 2016, he was even highly cited. I have the statement here. Let me see if I have it. Yeah, see it? I copied that from a published statement. Now, what's interesting, I told you he was killed by my friend, Braley. He's a really close friend. We worked together. We came up with the handbook of fixed point theory that was written by Braley and my late friend and mentor, Art Kirk. I wrote 2 chapters in that handbook. And it was a handbook of something I was trying to do online. I wanted to have a book online on fixed point theory available, and you can access it online in the 90s, early 90s. So I know very well Braley, very well. We were among the first ones to start what's known as the International Conference on Fixed Point. So I know what kind of mathematics he knows. I know very well. In fact, I will be talking about it this week. There is an open problem, which is still open, whether reflexive Banach spaces, they have the fixed point property for non-expansive mapping. problem is still open. And what's his name? Alspach gave a counterexample of an example of L1 and the weakly compact L1, capital L1, and the weakly compact convex sets and the non-expansive mapping without fixed point. It's very interesting. I really urge you to look for this paper. I mean, I do have it, by the way, but it's commonly, it's 2 pages. 2 pages in the Proceedings of the IMS. 2 pages, 1979, 1980. Huh? These 2 pages, I challenge as a conjecture anyone to simplify this example even in 10, 20 pages. Go ahead and explain to us. Number 1. Number 2, can we find simpler examples? None, till today. Now, Brayley wrote a book on these 2 pages. A book on these 2 pages. I know what Brayley knows. Okay? This is not a joke. Wait a minute, Brayley. How on earth did you kill Ziad? How? How did you allow Ziad to work only on G matrix? Why you did not teach him more on fixed point theory? The whole fixed point theory for Ziad is G matrix. Till today. In fact, I was looking for him yesterday. His work, it's still related to this G matrix space. In fact, journals are now not publishing on papers on G matrix. So you see the problem where it is. It gives you what? The easiness of publishing, but it limits you in terms of knowledge and what you can do. This is the problem. Everybody will know your name only through your work. They will not know you physically as a good person. They will not. They will only know your work. So my point is, one has to be extremely careful. So to move on this, I got interested into what? Working with someone in France. He just passed away, by the way. And his name is Maurice Pouzet. The last year of my PhD, I visited him in Lyon. And we were looking at the issue of the distance. What is a distance? Who asked this question before? You know the answer. Who asked this question before? Okay, fine. I'm not going to give you a hard time. I gave you a hard time earlier, so now I'm not going to give you a hard time. It was Adamar who asked what? Fréchet to find the distance between what? 2 functions. And I did tell you why. Because 2 functions, this question came after Lebesgue measure theory, and now functions are no longer in the traditional way functions, and therefore you are looking at the distance between 2 sets. So the question does make sense. It wasn't like they knew about the norms, some norms, in the case of continuous functions, L2 and so on and so forth. But he wanted more general case. So the question, in fact, if I rephrase it, was the écart between 2 functions. But if I want to rephrase it, what is the distance? Now we have axiom 1, 2, and 3. No, it's not working. It's not working. Can we find something bigger? Motivation. Motivation. You want motivation? What if I tell you now the work, this work, and this work are close? Okay. Now we have these crazy tools that tells you, 30% similarity. Yes or no? And when you publish your paper, they say 30% similarity, 40% similarity. And then you lose your mind, because in mathematics, we use D for distance, X for variable, etc., etc. So the way it is done is completely off. So how am I going to take a poem, another poem, and the 2 poems are close to each other? Okay, want me to give you better? What about if I take a program and another program and see how close they are? These fundamental questions are still, till today, people are working on them. So when I start working with Maurice on this, it wasn't just for the sake of coming up with what? With a structure that will capture what? The tools by Banach. No. The idea was, let us try to go deeper. Shoke gave an answer. Hosdorf took it over. He gave it to us, and we have it. Let's go beyond that. What would be the distance? 30 years in the making. We just came up with an epsilon answer. 30 years, 3-0. Okay? And our paper, when we submitted this paper, it was sent back to us, saying, please, shorten it. It was too big, too big. So let me see if I can. So this is the paper, as you can see there. It came in 2020. And I wanted to pay attention to this one here. So the distance from x to y less than r. Okay? See, this is a relation between x and y. So I'm looking at r as a number, but as a relation. And I say that x, y, the pairs, belongs to r. In your mind, it means this. Of course, not, this is the classical view of the distance. View of now the distance. And of course, we put somewhat conditions. I'll put this, and I want to show you something. Yeah, so here we have all the formal definition under this idea of relations instead of numbers and so on and so forth. Since I want just to show you something here interesting. Okay, now, you see the ball? So remember what I told you. The distance from x to y less than what? R. But now is no longer distance between x and y. It's now a relation, yes? So R is the relation. So you have the ball, but it's a different concept of balls. Now let's go back here. What is the diameter of a set? It's no longer a number. So we have the diameter as being what? A set now. Okay? And of course, we looked at what? Some cases where this structure is more appropriate. It's really interesting, very interesting paper. I urge you to read it if you have time. Don't. Great, so let's move on. And now I get into something serious. Let's move on from the generalized metric and so on and so forth. So now I want to jump to 1973. In Jamia Islamia last year, September 23, as well as here, by the way, I gave them a talk. Okay? And the talk was, what was it, Izhar? Good question? Oh, I forgot. Wallahi, I forgot. What was it? Yeah, something like that. Yeah, it was, what is a good question, mathematically speaking? Okay? What is a good question? Okay? And what comes to mind is a good question is a hard question. Okay? Earlier today, our friend was talking about Fermat's theorem or Fermat's conjecture, and it's a hard question. Therefore, it's a good question. This is common sense. It's a hard question, therefore, it's a good question. So what I did, I gave them a talk to make them change their mind. A good question may not be a hard question. A good question is once we see the answer of the question. Once we see the answer, then we can see, oh, that was a good question. Or that was a useless question. James came to do his PhD with Kirk. And Kirk asked him a question. Very intriguing question. He told him, can you find? So, first of all, look at the statement I put here. Among the deepest what? Extensions of the Banach contraction principle. The deepest one. And in fact, since I started working in fixed point theory, 1984, till today, I am still puzzled by the work of James Till today. So it shows you how profound this is. It's not artificial. Now, the question was, listen to this. The question was, can you find a new proof to Banach contraction principle? 72. When was the theorem published of Banach? By now you know. 22. 1922, 1972, 50 years. I assure you, without exaggeration, thousands of pages are written on the Banach between this period. No exaggeration. So, how on earth, me, as a PhD advisor, I'm going to ask these new students to find me what? A new proof of Banach action plan. How? Crazy. Why it's crazy? It's crazy. It's a good question or a bad question? It was my essence of my talk. I gave a Jamia Islamiyya as well as here and all over the world. Because I always prepare one talk every 6 months. Was it a good question or a bad question? Don't know. So James, he took the question and starts working on it. Ah, I forgot. Why did Kirk ask him this question? Very important. Forget about James. Why Art asked him this question? You will not find an answer published. You can only find the answer if you sit with Art, have dinner, he drinks, because he loves to drink, and then he relaxes, and he's happy, and you ask him this question. You ask him this question. Hey, Art, why did you ask James this question? You understand what I mean? So, my AI assistant will not know the answer. Connect what I was telling you earlier. Okay? So the answer was, he wanted to take a route that was not there. He wanted to find a different route that nobody took. Why? Because the classical routes, thousands of people took it. They chose them. What do you want to find more? Anything you want to think of, they already did it. So finding a different route allows us to look at the problem from a different what? Angle, different what? Direction. Do you understand now? It wasn't just find me a different proof. No, 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 no. It's more to the story than what can be interpreted from the question. Ready? Let me show you what James did. Okay? Okay. So this is James. Okay? He started by looking at this. Now, why? You are not going to find the answer anyway. The AI assistant will not know. Period. Why? Why did James start like this? Why? Okay. The answer is, if you go back to the proof of the Banach contraction principle, what does it say? The classical proof. I'm talking about whether it's Banach or the one before known to our friend, what's his name? Picard or Liouville or whatever. It doesn't matter. How? And I did tell you earlier today. What do? Input, output, and what? You iterate. You loop it. Yes or no? So the problem of the fixed point is where? Is only by looking at what? At a point. You start what? Looping. You start what? Iterating, and then hoping what? That it will go where? To the fixed point. You understand now? So we are just looking at what? At the orbit. Just x, t of x, t squared of x, etc., etc. Do you understand now why he was looking at t squared and tx? Otherwise, it doesn't make sense. Let's continue. He added this term here, this term here. Yeah? No problem. Then, he moved this one to the other side, and this one to this side. You will find 1 minus k times dx dx, and here you will find this minus this. Divide by 1 minus k, k is less than 1, and you end up having this inequality. Yes? Are we okay? How many steps? Huh? How many steps? 2, 3, to be generous? Huh? No big deal. So, is the question hard or easy? I just told you, hard question that nobody can answer. Oh, it's a good question. What kind of question is this? That you are using something as simple as this. Yes or no? Shall we continue? Let's continue. I want you to pay attention to this. What's this? This is a function of x. Why did I say x, not tx? Because if I replace x, this one, do you see it? It's the same function here of x, here of tx. Therefore, what do you have here? You have a function of x minus a function of x minus a function of tx. Okay. Let's move on. You see it? So I have the distance from x to tx less or equal than phi of x minus phi of tx. Let's try to understand this. Now, let me take you a little bit down to understand this business. First of all, do you see phi of x minus phi of greater than the distance from x to tx? Therefore, it has to be positive because the distance is positive. Yes or no? Therefore, phi of x is greater than what? Phi of t of x. Okay, let's look at phi as the level of energy. So you take a particle, you excite it, magnetic field or electrical field, it starts to get excited, and then when it's excited, it moves to the next layer. But the effect is to lower your level of what? Of energy. Do we agree on this? Do you see it? So, why? Because if you don't see it this way, you will not understand what Economcs says. So try to follow me now. So you take a particle, you excite it. The effect of the excitement, experiment. Then it moves, but it moves to a layer with lower energy. Yeah? So far so good? What happened when you reach the lowest layer of energy? Wait, follow me. What is the function? What's the function? Function is 1 over 1 minus k, distance from x to tx. Yes? K is less than 1. Therefore, this function is what? What can you tell me about the function? This function. Because this is phi of x. What can you tell me about this function? Very important. What can you tell me about this function? Positive. Yes or no? Huh. So if the function is positive, which is the energy. If the function is positive, and you are lowering what? The level of energy. What happens if you keep doing it? What happens if you keep lowering what? The level of energy. Okay? If you're lucky, and you reach what? Because you are positive. Therefore, you reach what? No, that will be ideal. Ideal to get to the level 0. But let's assume we reach the lowest level of what? Of energy. In fact, that's what happens. You will never reach what? Level 0 because you don't lose energy. Okay? So you just get to the lowest level of energy. Lowest level. Okay, we are mathematicians. What does that mean? The infimum. Function is what? Positive. I have an infimum. Go down, closer to the infimum, till you reach the infimum. I assume you reach the infimum. What happened to you when you are at the infimum? And you excite again the particle. Where is it going to go? Nowhere. Because you are at the minimum of the energy. Oh. What happened? Now, I'm exciting the particle. I am at the lowest level. Yeah? I know that this one, once I excited the particle, this level of energy will be less than this one. But you are at the infimum. Therefore, what happened? This one and this one are what? Same. Because you cannot go below the lowest level of energy. But if they're the same, what happened? What happened if this is the same? What happened? This will become what? 0. And if this is equal to 0, what happened? So your particle doesn't move. It stays exactly what it is. Okay, in our fancy wording, T of x equal x means what? You got the idea? Now, in general, fine. So here you see it. Positive. It doesn't have to be positive. But I need to be what? No. I need to have what? Some lower what? Because otherwise, if I'm not careful, and they keep going down, I will go where? Minus infinity. I don't want to go to minus infinity. And therefore, I just need what? To be bounded what? So let's say you are bigger than C. Yeah? Yeah? You are bigger than C. What happens if you take phi minus C? This problem is invariant. Whether you are taking phi minus C. The problem is invariant. Yes or no? It's going to be phi minus C here, phi minus C here, minus C plus C. C is gone. Therefore, assuming that phi is what? Positive. Or bounded below is exactly the same. Do you agree on this? Okay, number one. I'm taking you into the mind of what? Of characteristic. It gets complicated. What if I take T of x equal x? What's the name of this? Huh? No. Everywhere. T of x equal x. What's the name? Thank you. Identity map. Yes? Huh? T of x equal x. What happened to my inequality? Huh? So, quality is what? T of x equal x. What do I get here? T of x equal x. What do I get here? Therefore, your T satisfied. Now, what's the problem? What did I tell you? The question was to find what? What Kirk asked James? Find another proof to what? By playing, he came up a few steps to this problem that you see on the screen. And then he said, wait a minute. T equal identity satisfied. But guess what? T equal identity failed the Banach contraction principle. Why? Because it's not a contraction, and we don't have uniqueness at the fixed point. Everything is fixed. What does it mean? Did he fail? Did he abandon? No. He just discovered a new class of mapping. Contractions are one of them, but not only contractions. You see now? But the question is now, change. Change. What's the question now? Do we have a fixed point? So it's no longer, he knows, it's not going to be Banach contraction. Oh, it's gone. It's more general than what? Banach contraction principle. Question is, do we have a fixed point? Now, wallahi, I told you, this problem of Karisti and the paper that came up in '76, till today, I am puzzled by some of the facets of this theory. Till today, we're talking about almost 50 years. Yeah, 50 years, because it was '74 when it was submitted. Now, let's start with the orbit. Let's take a map. I called it C. I am the one who called them C. A long time ago, by the way. Why? You know why. Class C. You know why. Christie. So by respect to his work, I didn't call them K, camp. No, C, class. So let's start with X. Ready? Are you with me? Let's start with T of X. We have that. What about T squared of X? Then what happens? What you're going to find is phi T squared of X is less than phi of T of X, less than 3 of X. So the level of energy now is going down. Yes? And because D satisfies the triangular inequality, you have also the distance from T from X to T squared less or equal than. Okay. Now, let's continue now. Continue. What happened to the sequence Xn, which is the orbit? We can easily show that it is Cauchy. Triangular inequality and the equality you see there. You can show it's the famous telescoping series. You remember this from calculus? It's Cauchy. Therefore, it's Cauchy. Therefore, why does it converge? It converges because, good job. So number one, I need phi to be bounded what? Below? Good job. Number one. Number two, I need the metric space to be what? Complete. Good for you. Now, are we assuming some weird assumption? No. No. Why? Because what is the Banach contraction principle? The metric space is complete. T is a contraction. You have a fixed point. Yes or no? So we're not coming up with some weird assumption. No, no, no. Great. So now we take what? The orbit. It's Cauchy. Therefore, it's convergence. Because I'm assuming what? Completeness. What happens to the limit? In the case of what? Banach, the limit is a fixed point. Why? Because T is continuous. You understand? We use the fact T is Lipschitzian, is continuous, we're done. What happened here? I built an example, James, that T may not be what? And it satisfies that. So in his class, this new class of mapping, not necessarily you are continuous. If you are not continuous, the limit may not be what? Point. Now, James throw the towel. Yeah. He got stuck. He reaches what? Omega. And he said, what can I do? He knew that T may not be what? Continuous. And therefore, he did not know what to do. Lucky him. He was a student of whom? Here. And what is famous about here? He uses transfinite orbit like bread and butter. Like here, if you want, rice. It is tool of daily research. James did not know that. I did not know that. I learned it from here. So, what does it mean? This is very interesting for you because you don't like ordinals, and it's a big mistake. So, look what happened. Start with x. x0 here. x1, which is t of x. x2 is n. Omega. Is it converged? Okay? If everything is good, which is the case here, that omega may not be fixed. Okay, fine. Let's take what? Continue. T of omega. And then what? T squared of omega. So that's using what's known as transfinite what? Orbit. We are going beyond the first countable, the classical orbit. We're going beyond the classical orbit. Okay, if you keep going, this function phi keeps going down. You see, this phi with the orbit, transfinite orbit, keeps going down. Guess what? It's a property of the real numbers. You cannot keep going down forever. If you have, with every ordinal, you cannot exceed the cardinality of. So now we're getting into something that James did not know. It was what? Kirk who helped him out. Said, okay, don't worry, I know what to do. We can keep going. If you go to my book, and I know that the book was sent to you by Javid, if you go to the end of that book with Kirk, if you look at the end, we put an appendix that discusses this, what I'm talking about. On the real line, you cannot have increasing with decreasing numbers with indexes from all ordinals. They have to what? Eventually what? Become constant. They have to stop. They have to saturate. What does it mean that there is an x alpha equal to x alpha plus equal to all of them? But x alpha plus is what? T of x alpha. Therefore, what happens? X alpha equal T of x alpha. Therefore, we reach what? In order to do this, to keep going, you need one more assumption. It's in the proof, but one more assumption, which is what? That this function phi is lower semi-continuous. I can show you the technicalities, but as I told you, don't. Think about it, and you can read it and understand what I'm talking about. So you need the lower semi-continuity to keep going. Number one, if I take an orbit, normal, countable one, it's Cauchy. I need to converge. If I need to converge, I need to assume that MD is what? Complete. What else do I need? Phi, not to go to minus infinity. Therefore, I need phi to be what? Bounded below. Okay? And I told you whether you assume bounded below or positive is the same. Great. And what else? You need phi to be lower semi-continuous for this orbit to be transfinite and keep going. You have fixed point. Period. Oh, I'm sorry. Oh. Why? Why did you go that fast? Oh. Okay. So do you see it now? And D is what? Complete. Function phi is positive, bounded below. Lower semi-continuous. T satisfies this, condition C. Therefore, T has what? Do we have 1? No. Identity will work. So you don't have 1. Do I have the fixed point after countable iteration? No. You may have to go beyond countable iteration. Oh, no, wait. I love when my students, they take it for granted. told you I'm still till today pondering on this theorem, puzzled by this theorem. What did they tell you? What was the question from Art? So always, and you are going to be seeing this for the next 4 or 5 days, I want you always to go and think what? I will say it every day. Think what? Outside of what? Don't be like the AI, my AI assistant, who only thinks inside the box. I want you to think beyond the box. What was the question from Art? It was, find another proof of the Banach contraction principle. Look where he is now. Do you understand the essence of the question? This is what I'm trying to tell you. The essence of the question. The essence of the question was what? Can we find a different route that can teach us something what? Different. Oh, by the way, the energy explanation I gave you, that was not Art or James. No. So you see now, we have a new what? A new window. A new window that nobody saw before. Why? Because they went the traditional way. They went the route that was everybody took. By taking this different route, they saw, like for example, what they say, the tree or trees that hide what behind it? The forest. So the paper was what? They looked for an example. And this connects what? Let me just tell you, without going to details. I didn't put it by the way. This condition connects x with tx. Why does it fail continuity? Why? Because it doesn't tell you what's going on between x and y. Continuity means x close to y. T of x close to what? T of y. But here, you only have a relation between what? X and tx. How? There is no way you are going to be able, from this condition, to tell me that if x is close to y, t of x is close to ty. No way. Anything that connects x and tx, that's maybe what? A tool to use. This category of mappings, we call them inward mappings. Inward mappings are mappings that connects x with tx. Without going to details, I didn't put it because that wasn't the purpose. I want to convey another message, that's why. I didn't want, you can find it. So he published this theorem, 2 more papers on inward, defended his PhD, and after that he became a cowboy for years in Texas. Why is that? It's amazing what he discovered. Why he became a cowboy. Now, all what I said is here. All what I explained to you is written here. And this PDF file, they have it, as well as my lecture notes. Okay? The whole course is based on this lecture note that I was writing just before coming. They have it as well. It's there. Okay. So let's continue. Now, that's what I said, 1974. Published in 1976. Okay? At the same time, 1974, Eklund published a paper. And he published this theorem. Do you see the reference? Yes? 1974. So, Ivar Eklund was my master thesis advisor. Okay? At École Polytechnique, when I did my senior thesis, I did it with him, with Ivar Eklund. So, I know very well Eklund. Okay? So he's not like somebody I'm going to trash or somebody I'm going to say something bad about him. No, he was my advisor. Okay? And he was a wonderful person. In fact, he's a wonderful person. there is more to the story about him in France and so on and so forth, and how he behaves with Muslims and so on and so forth. But that's not, I'm not talking about him being a good man or a bad man. I'm only talking about what? Math. In mathematics, we don't have this feeling, emotions. Oh, you are a good man, therefore. No, wait. Mathematics is one thing. You are a good man is something else. Yes? Huh? I can tell you you are wrong, mathematically speaking, and they can love you for the sake of. Yes? No problem. Now, to publish this, look at this statement. Now, what do you see in common? You see a complete matrix space. Yes or no? And you see the function phi, which is what? And it is what? Also positive. Yes or no? But there is no fixed point. Yes or no? There is no fixed point. So, on Caristi's paper, the conclusion is a fixed point theorem. On Eklund's paper, it's nothing, there is no fixed point. Now, I want you to pay attention to something that you did not see. So I'm going to give you a few seconds. Ponder on the reference of Eklund. Okay? Ponder on the reference of the paper by Eklund. Okay? Do you see something? Tell me. Something that got your attention. Anyone? So, I mean, in fact, one question per day. Huh? I already gave you hard time earlier today. I'm not going to give you hard time now. Okay? So let's move on. How many pages is that paper? How many pages? Huh? How many pages? Okay, you have it. 324 to 3 what? 53. So almost what? 50 pages. Now, I swear, this paper is one of the most beautiful paper ever. Now, what is special about that paper is what he discovered. The application. Okay, wait. Let's go back to Caristi. What did we say that Caristi did? With his theorem. He only did what? You remember the technical name? Inward mapping. And that's it. This guy, he blew it. In fact, to a point where in this university, one of your faculty came up with a journal dedicated to this theorem. This theorem. Conference in 2023 here at Aligarh was entirely dedicated to this theorem. This theorem has now school worldwide. This theorem. Not Caristi. This theorem. Why, I mean, are you insisting on connecting the two? Why? Why are you talking about Caristi and Eklund? Why are you insisting? Okay, if you go back to Caristi paper, you will see in the Caristi paper when it was submitted. But if you go back to this, you don't see when. Let's move on. I still have something for you. That's why he became a cowboy. Now, to understand this, both. Oh, by the way, here are. I just did this yesterday, by the way. Okay, so it gives you an idea. Look at the first one. The first one is a book, by the way. Okay, and for your information, Tamam is one of the biggest mathematicians, applied mathematicians in France. Okay, so if you look at the book, is what 7,000 what citations. And listen, this is not about some playing with citations. No means, none whatsoever. These are real citations to real mathematics. Okay? Look at, these are the top ones for Eklund, the top ones. So look at this one, This is the famous one, huh? The one I just showed you, yeah? Huh? 3,104 citations. Okay? And then problem variationnel, another one, and non-convex mathematics. All of his work, and this guy has done tremendous work. I mean, on economics and on tremendous body of work. I'm talking about Eklund, okay? But you see, the top ones are all related to what? To the variation of what? The theorem I just showed you. Okay? So it showed you the importance of that theorem. Now, of course, if I show you this theorem, it means nothing to you. Let me make it now baby for you. Ready? First, if you look at it, it means, wow. Let me make it for you piece of cake. Okay? Why? Because once you understand it from a piece of cake point of view, you will understand what's going on between what? James and Eklund. You understand now? Let's do it. Ready? Oh, these are the applications of that theorem. Profound applications, not inward mapping. Let's move on. Now, what did they write in red? That this theorem, Caristi, as well as Eklund, especially Caristi theorem, for me, I spent so many years working. So many years. I did not publish within 2 weeks. I did not publish within a month. Years working on this theorem. And what did they put there? Still, I am puzzled by some of the sides of Caristi's theorem. Okay? So, what is behind both Eklund and Caristi? Eklund saw it. Caristi did not see it. That's fine. What did they see? He saw something that was popular by Bronsted. But it wasn't Bronsted. The first one who used that tool was Bishop and Phelps in that paper, 1963. But the one who got the tool out from that paper, 63, and made it popular is Bishop. Because of that, this tool now bears the name of Bishop. You understand? It's originally where? In Bishop and Phelps' paper. Okay? You understand. Don't worry about it. It's a very simple tool. It's not like something fancy. No, just give me a second. Ready? Let me show you the tool. Here it is. So what do we have? Do you see the connection now? We have what? We have what? Metric space? Yes? We have function what? What? 0 plus infinity. So we have what? Same stuff used by Caristi and Eklund. Yes or no? Same. Forget about the assumption, completeness, and lower to continuity. But what you have in your hand, both of them are using it. Metric space and this function phi. Now, this order has a name. What do we call it? What do we call it? What do we call it? I swear I didn't hear you. No. Bronsted order. We call it Bronsted order. Who discovered it and used it? Bishop and Phelps, 63. Who made it more in applied analysis, and so on and so forth? Bronsted. So now look at this. X less or equal than y, if and only if we have this. So this inequality that is of metric nature becomes now discrete in metric. You need this. So now we are no longer what? We're no longer talking about what? About metric business. We're talking about discrete. We're going to discrete set now. Go back to Kirk. What did Kirk ask James? He told him, please try to find another proof to what? Banach contraction principle. Look at this window or the door that James opened. Hey, why aren't you talking about Ikram? I'll tell you in a second. Give me a second. So he opened the door. He opened the door. Look now where we are. We're talking about what? Looking at this problem from a discrete point of view. We're no longer looking at the problem from what? From a continuum point of view. Let's take now, by the way, it is a partial order. So I'll leave it to you to show that you cannot have x less than y, y less than x, because this will give you what? Phi minus y minus phi of x, phi of x minus phi of y, or 0 is going to be negative, and therefore it's equal to 0, therefore x is equal to 1. Okay? Huh? So you have the anti-symmetry, and you have the transitivity because x less than y, y less than z, x less than z because of the triangle inequality. Okay? As long as d is additive because of the triangle inequality, you get a partial order. So it's a partial order. Okay, fine. Now, we have an order. Now we have to think in discrete set theory. Huh? Forget about what? Huh? Functional analysis. You are here now. You have to go back to your classes in discrete sets. Okay? What do we have in discrete sets? We have the concept of minimum, infimum, supremum, maximum. But you may not think of it like, for example, the set of subsets n. Yes? What's the minimum? Empty set for the inclusion. Huh? And what's the maximum? N, the entire set. But what if I remove the what happens? I remove the empty set. What happens? You have what's known as minimal. So singleton will not be the minimum, but there will be what's known as minimal point. Meaning what? Nothing below them. Yes or no? Huh? And the same goes for what? Maximum point. Are you with me now? Discrete set. You teach this to any student, senior math student. Huh? When do we have a minimal point or maximum? Yalla, please, tell me. Yalla. When do we have minimal point or maximal point? When? Huh? One word. Two words, but that's great. Good job. Yeah, zone. Yeah. Zone is the tool that tells you you have what? A minimal or maximum. Okay, how? What are the assumptions of zone lemma? If you have a totally ordered chain, okay? Chain. You have what? A lower bound. You have minimal. Or if you say any chain, totally ordered chain, you have what? An upper bound, you have a maximum. That's zone lemma. Yes? Are we okay? No problem? Do we need zone lemma to have minimal and maximal? No. Let's take two trees. And by the way, they call them trees. Okay? Two trees. One has a root, one does not have a root. Are you with me? Basically, if you want, they call them trees, by the way, huh? In discrete sets, and forests. Let's call it, for us, two subsets. One is totally ordered, with no minimum, no lower, no upper. An infinite like R. And the other one has a root, in other words, minimum. Are we in? Okay. This minimum is minimum. And by the way, they are not connected. In other words, they are not comparable elements. Any element in this tree is not compared to this element. Okay? So only these ones are comparable, and these ones are comparable. This element, the root here, is a minimal point. But you see, this set of these two trees fails zone lemma. Why? Because of this one. You have a chain, but you don't have a lower bound. So zone is too strong to give you what? Minimal point, maximal point. But you may have minimal and maximal without having what? All the chains having lower bound or upper bound. Are we in? Okay. So now that I say this, sorry. Let's look at now minimal. So this definition of minimal. X tilde is minimal. Anything below it is equal to it. Yes? That's the definition. Now look at the theorem next. Now you will understand. It's nothing. Yes or no? I'm not showing you something fancy. Yeah? You agree with me? No? Any student who took a little bit of math knows what I just said about discrete and partial order. Yes? Huh? Okay. So now let's continue. And I will stop there anyway. Oh, yeah. Okay. Pay attention now. Now let me show you how baby it is now. Everything comes collapsing. Ready? So we have Bronsted order. This is Bronsted order, yes? You remember the definition, yes? Huh? And look at now. Look at T. I want to show you something. Look at T. T goes from N to M. A map. Such that T of X is less than X. For the Bronsted order. If X tilde is a minimal element, T of X tilde is less than X tilde. Therefore, T of X tilde equal X tilde. Meaning what? That minimal is fixed point of T. Yes? Therefore, what's that? That's carries T. Yes or no? Shall we continue? So, first part 1. That's carries T. So remember, you have to remember, what does it mean this? This means the distance from X to Tx is less or equal than phi of X minus phi of Tx. You remember the Bronsted order. Let's go to 2 now. Ready for 2? 2. Let's take X, which is different from the minimal. You cannot be below it if you are different. You cannot be below. What does it mean, not below X tilde? But it means exactly what you have here. That's a clone. But a clone has an epsilon. Has an epsilon here. But guess what? The whole theory, instead of working with D, I can work with epsilon D. It doesn't matter. If I multiply the distance by an epsilon, the whole essentials are the same. Completeness, everything, continuity, because you are multiplying by a number. And therefore, to have it D, or to have it with epsilon times D, epsilon is fixed. It's the same. Makes no difference. Now, statement 1, carries T. Statement 2, echelon. Oh, wait. Don't think. Oh, wait. What was X tilde? Tell me again about it. Look at it in the theorem. What is X tilde? It's a minimal of what? Of the Bronsted order. So it's the same element in the conclusion of what? Carries T? Same element in the conclusion of what? Oh, maybe there is something there. So who is the first one? Are they at the same time, independent of each other, or not? It happens to be not. Our friend Ekron, my good advisor, got access to the paper by Christie. Once he got access of the paper by Christie, he saw the profoundness of the work done by Christie. Now, when he published his paper, there is nowhere to be seen the ideas of what? Christie. Because the ideas of Christie are all based on a map. His work is totally different. What happened to Christie? Why he gave up? Why he did not give him what? Credit. He was so disgusted that he went to his farm in Texas and he became a cowboy. Now, what if Ivan decided to say that he got the idea from Charistes? It will not take anything from his work, because his work is so profound that it could have been just giving him what? Credit. But he didn't do it. What's the lesson from it? Big names are not to be trusted as being above our human behavior. They can also be nasty and kind. Let's maybe conclude here. I'm going to conclude. How do we get the minimal point? I will conclude here. How do we get the minimal point? You just told me. Huh? By zone. Yes? If we have zone, we have minimal point. Guess what? We have zone if and only if you have it. You see this figure? We have zone if we assume complete matrix space and phi lower symmetry. So the main assumption in Charistes and in Echelon, they gave me what? Zone lemma, therefore minimal point, therefore the conclusion I just told you. But wait, and I will leave you with this. I just told you, remember the trees. You don't need zone lemma to have what? Minimal. Meaning what? That maybe the assumptions, completeness, and lower somatic continuity are not optimal. What are these optimal? Till today, nobody knows. Thank you very much.